We will wait 3 more minutes and then start. We will start in 2 minutes. All right, good morning class. We'll start now. Sorry, I could not turn on my video today. There's some problem with the camera, but let's get into the course. So last lecture, we looked at design of gravity dams, and this week we are going to start earthen dams. And we also started a tutorial on gravity dams. If you have not started yet, you will be doing it either today or in the next tutorial. And for the solutions for this tutorial would be released on Friday or Saturday for the gravity dams. There are a total of 12 questions in the tutorial. So the first 4 solutions would be available on this weekend. And once we finish the syllabus on earthen dams, then the solution for questions 5 to 11 would be made available after that. And the last question is related to spillways. So once we cover the spillway concepts, then you can work on the problem and we will also release the solution. So before beginning earthen dams, I just wanted to show you the galleries inside a gravity dam. So in the last lecture, we spoke about galleries inside a gravity dam that are usually provided to drain water that seeps through the dam material or through the foundation. Now, if we provide the galleries, then it is going to relieve that uplift pressure. And this is what a gallery looks like inside a dam. So it's going to be a small passage, and you can see here there's a small channel that can drain the water, whatever is seeping through the walls. And people can walk through this if they want to do some maintenance works inside the dam or to check the structural integrity of the dam through non-intrusive methods. And they also provide visits for visitors like us. If we go on a field trip, then we can go inside a dam to have a look. So this is what the galleries inside a dam look like. Now we will start on earthen dams, and as the title says, earthen dams. So these dams are made of natural materials like soil or rocks, and these are one of the oldest type of embankments that are being in existence. So earlier, before the engineering, people used to build dams so that they could store water. So they used to build earthen dams. And later on, with the advancement in knowledge, now we have some design principles on how to properly and safely design an earthen dam. And that is what we are going to look in this module on how to design earthen dams. Since this is made of natural materials like soil, these kinds of dams are prone to damages or failures easily compared to gravity dams. And we will be looking at the causes of failure for these earthen dams as well. Now, the first is the types of earthen dams. So there are three types of earthen dams. So one is the homogeneous embankment type. So this is quite intuitive from the name itself. So it says homogeneous, meaning the whole dam is made of the same material. And you might have seen these earthen dams or embankments whenever you travel, for example, from Prayagraj to somewhere else. You might come across these embankments for small lakes or even small reservoirs. So, and I have also shown you one of the pictures of the earthen dams in the first few lectures. So this is the typical section of an earthen dam. So you have side slopes on the upstream and the downstream, and then you have a flat top width. And you have some water on the upstream, there could be some water on the downstream. So the dimensions of this earthen dam are generally based on some rule of thumb. So there are no guidelines on there. There are some guidelines, but there are no design principles on what should be the preliminary section of an earthen dam. So it is based on trial and error. So we first start with some rule of thumb on what should be the top width, what should be the side slopes, and we then check for the stability of the dam. So if the dam is stable, then that is good. If the dam is not stable, then we need to revise our dimensions for the dam and check for the stability again. Now, one of the major problems of this type of dams is the seepage. Since the material that we use here is porous, then the water can easily seep through the material, and that is going to create some problems in the embankment section. And usually, for example, if we do not provide any drainage facility, then we need to have very larger widths of the embankment to make sure there is no failure because of seepage. Now, you see, if there is water up to certain level on upstream, then the water is slowly going to seep through the soil, and this is what you would see as the seepage line. So below this seepage line, the water is going to be saturated, and above you would see some capillary action or negative pressures. And as the water seeps through this, it could probably create some piping action, meaning it can erode the material as it exits the embankment. And if it is eroding, then slowly you would start losing material on the downstream side, and this is going to destabilize the dam itself. So that is why it is important to provide drainage in the embankment dam. So that is what you see here is we have the same embankment section, but what we do is provide a drainage filter. So now whatever the water is seeping through the dam would be released through the drainage. So you would not have the problem of piping or erosion on the downstream end. So that is why we provide a drainage filter. It could be made of coarse materials. And some cases on the upstream, the slope could be unstable, and to protect that slope, you can also provide some protection measures like riprap. So riprap is just you place the stones or rocks on top of the slope, and that will stabilize the slope and also reduce the erosion because of the upstream water level. Now, if you remember in the last gravity dams, we discussed about winds and the effect of wind on the gravity dam. So if the wind is blowing on top of the water surface, it is going to generate waves in the reservoir. So these waves are going to create some turbulence on the slope of the embankment. Now this turbulence can erode soil or the sediments on the upstream slope, which would cause the failure of the dam. So to prevent that, we provide a riprap, which is stones or rocks placed. What these stones or rocks do is to reduce the energy of the waves, and in turn we are reducing the turbulence and the erosion because of this wind waves. So that is why we provide some protection on the upstream, and it may be necessary to provide some protection on the downstream as well for some of the scenarios. And the second type of embankments is the zoned embankment type. So earlier what we saw was homogeneous. So meaning the whole section of the dam was made of single type of material, which could be a soil. Now, in the zoned embankments, what we have is two zones within the embankment section. So this is the soil as previous case, but here you also have another layer which is impervious. So the soil is pervious in the outer zone, and in the inner zone it is impervious, so that you can divert the seepage from the pervious zone through this intermediate zone to the downstream. So what you are doing is to minimize the seepage through the entire section of the dam. So instead of allowing the water to seep through the entire section of the dam, you are restricting the seepage only through the medial core section, or the transition filter that you provide in between the impervious and the pervious sections. Now, the impervious core could be made of clay, or it could be silt or silty clay, so that you are reducing the seepage capacity in the inner zone. And the third type of dams is a diaphragm type of embankment. So this diaphragm is similar to a column or a core that you provide in the middle of the dam section, and this is usually going to be impervious and made of steel or concrete or timber, so that there's no direct seepage from upstream to the downstream, and you can drain the water by providing a drainage filter as well. And usually the thickness of the diaphragm is kept less than 3 meters. So if the thickness of the diaphragm is more than 3 meters, then it would be considered a zoned embankment. So for a diaphragm embankment, the thickness of the diaphragm should be less than 3 meters. And then how do we construct these earthen dams? There are two methods on how you can construct the earthen dams. One is by hydraulic fill method, and the other is the roller method. So the hydraulic fill method is simply you lay pipes of where you want to construct the dam, and along those pipes what you feed is a mix of water and the soil material that is going to be discharged at the site where you want to construct the dam. Now, as the material is getting deposited, then the material would consolidate on itself. We are not providing any external consolidation or compaction of the materials. And since the transport of the materials is dependent on the size of the materials, if you have coarser sands, then they are going to be deposited near the outlet of the pipe, whereas the finer materials are going to be transported longer distances, because the coarser materials have the tendency to settle down. You would require higher velocities to keep the coarser materials moving through the pipe. And for example, you're releasing this mix of water and sand at a speed or velocity of 1 meter per second, then the coarse materials might be getting deposited near the inlet edge, and the finer materials might be getting deposited towards the end of the section. And since the material is going to be saturated with water, there is a problem of high pore pressures being developed. And also, because we are not providing any external compaction or consolidation, the soil material can settle over a period of time slowly. So you need to take that into account as well when constructing these types of embankments. And the second method is rolled field method, where now you are constructing the embankment at different stages. So first you place the materials up to a certain height, and then you compact them by using rollers on top of it. And then once you compact the materials up to that certain level, then you place more materials on top of it. So let's say this is your embankment section that you want to construct. What you do is first place the materials up to this level or elevation, and then compact it using rollers. And in the second stage, you place materials on top of it up to this elevation, and then compact it. So you are constructing the embankment in stages, where you are compacting the materials using rollers at every stage. And because you are compacting this while construction, then the settlement is going to be lower later on. Now, what are the causes of failure for earthen dams? One is it could fail because of hydraulic failures. For example, you construct a section like this, and you have considered a design flood level up to this elevation, for example. Now, let us say this year there has been a torrential rain, and the flood level has increased very high. Then let's say this is your actual flood height. Then your embankment is not able to store the water. So what happens is the water is going to overflow on top of the embankment. Now, if the water is going on top of the embankment, the water has tendency to pick up sediments. Because the water flow has some energy, and that energy is going to erode the sediments, and because of the erosion of sediments on the embankment, you would see the embankment slowly getting eroded, and there could be failure of the embankment because of overtopping. And there could be erosion on the upstream face, as I mentioned earlier. Again, let's say this is your embankment and this is the designed fluid water level. Now, if there is heavy wind that is blowing in the reservoir, then you would have waves that start coming on the upstream face. And because of the turbulence of the waves, you would see erosion happening on the upstream face. So slowly the erosion would progress and then result in failure of the dam. And the third cause could be erosion on the downstream face because of gully formation. So let's say you have this embankment again, and let's say you have rainfall on the embankment. So the water is going to, whatever falls on the embankment surface is going to go down on the slopes. And in the process, it could pick up sediments as the water is going down the slopes. And because of this erosion of the sediments, you will see erosion on the downstream face of the embankment. So that is because of the rainfall. And because we don't want to have such a failure, what people generally do is to, let's say this is your upstream phase. On the downstream, you have a slope at different stages. So you provide a slope for certain elevation, and then you provide a horizontal section where the rainfall water can be collected and then drained from here. And then again, you have one more slope followed by a horizontal berm. So what you do again is whatever the excess rainfall is runoff, you're going to collect it and then drain it through the berm. So what you do is provide berms on the downstream face. And the other reason for the erosion of the downstream side or the downstream face is because of erosion at the downstream toe. Now this is the embankment, the water level, and the seepage line. So if we do not provide any drainage filters in the embankment, then the water is going to exit through the downstream face, and then you will see the erosion of the downstream face. Or sometimes what happens is you have some water level on the downstream. So you have tailwater level on the downstream, and there could be a failure of the downstream slope because of saturation of the soil as well. So to prevent this, what you do is you provide a drainage filter so that the seepage line does not go into the downstream face of the embankment. And then the second type of failures are the seepage failures. So here, let's say the first is piping through foundation. So you have this embankment, and let's say you are building the embankment on pervious soil. So which means the soil can allow seepage of water. Then slowly the water is going to seep through the foundation, and it is going to start erode, and it's going to go to the downstream. And in the process, it is going to erode the sediments here on the surface. So once it starts eroding here, then the erosion is going to progress towards the upstream, and that can lead to failure of the foundation and result in the failure of the embankment itself. So this is the piping through foundation. Then you have piping through the dam body itself. So you have, let's say, seepage of water, and then the water is exiting here, then you can see the erosion happening on the upstream face here. That would slowly progress, and it would increase in the amount of erosion and leads to the failure of the embankment. And the third is the slowing of the downstream toe. Again, there could be erosion here when the water is exiting the downstream face, and that is going to slowly erode the soil. And the third type of failures are the structural failures. Now, you construct the embankment on some foundation, and if the foundation soil is not able to withstand the stresses from the embankment, then the foundation is going to fail, and that can result in the whole failure of the upstream phase. There could be a huge slide on the upstream or the downstream, and which results in the failure of the dam itself. Or let us say you have some operating conditions for the reservoir. Let's say initially the water level is up to this certain level on the upstream, and if there is a sudden drawdown of water, you are suddenly releasing, for example, all of the water from the upstream towards downstream through a spillway, then the water level is going to drastically go down very fast in a shorter amount of time. Then your soil was initially saturated, so it had some pore pressure. Now you're releasing the water, meaning your water is also leaving the soil. So there could be failure on the upstream slope because of the sudden drawdown. Whereas on the downstream, it is the opposite. So for the downstream, the worst condition is when you have full reservoir on the upstream. So if you have full reservoir level on the upstream, then the water could seep through from the reservoir and then start eroding. So there could be a sudden failure of the downstream slope. Now, there are certain design criteria for earthen dams, and you need to keep in mind all of these criteria when you want to design an earthen dam. So the first is to make sure the permeability of the soil is minimum, or to make sure there is sufficient drainage through the embankment so that the failure of the downstream slope can be prevented. And there should not be any overtopping on top of the embankment. So the spillway that we design for the embankment should be sufficient to withdraw the water without any overtopping. And there should be sufficient freeboard. So earlier in gravity dams, we discussed about the freeboard, and we have also calculated what is the freeboard required for the upstream phase. Because we would have waves that are generated because of the wind that run up on the upstream phase. And to take that into account, we need to provide sufficient freeboard so that there is no overtopping. And the seepage line should be well within the downstream phase. So let's say this is your embankment. So your upstream water level is here, and the seepage should be like this. So here you have a drainage pillar that is going to drain the water safely. If the seepage line is going through the downstream, then this can pose problems of erosion on the downstream phase. So to avoid that, we should, whenever we design the earthen dam, we should make sure that the seepage line is well within the downstream phase of the dam. And also, there should not be, the material should not be very pervious so that there is free flow of water from upstream phase to downstream phase. So the permeability should be controlled. And the upstream phase should be protected against wave action by ripraps. As I showed you earlier, we can provide rocks on the upstream phase or even on the downstream phase so that you reduce the wave energy and in turn the turbulence generated because of the waves. And so you can reduce the failures on the upstream phase and also on the downstream. On the downstream, you provide some berms so that we can prevent erosion due to rainfall. And we should also make sure that a proper drainage filter is provided in the section of the embankment. So I also showed you that for upstream, the worst condition is when there is a sudden drawdown in the water. And for downstream, the worst condition is when there is full reservoir level on the upstream. So we should design the slopes such that they can withstand these worst conditions. And the upstream and the downstream slopes should provide sufficient bottom width for safety against shear stresses. So whatever the width that we provide for the embankment should be such that the stresses that are developed in the foundation are within the permissible or allowable shear stresses. So now we are going to start on the design of earthen dam. So in today's lecture, I'm going to discuss how we usually start selecting a section for the earthen dam. And in the next lecture, we are going to do the seepage analysis for earthen dams. And the lecture after that, we are going to do stability analysis. And probably in the final lecture, we would see how to control the seepage, and we will also discuss about rock-fill dams. So in total, we are going to spend 4 lectures on earthen dams. So the first thing when we want to decide the dimensions of earthen dam is to calculate the freeboard required on the upstream phase. So if you remember from gravity dams, we have HW, which is the wave height that is generated because of the winds on the reservoir. So this is your upstream, and you have water level here, and you have some winds blowing. So because of the wind, it's going to exert shear on the water surface. And this shear is going to generate waves that are going to run up on the upstream phase. Now we need to calculate what the wave height of this wind waves is going to be. So HW is the wind wave height. And we have seen in gravity dams how to calculate the wave height HW. So HW is a function of the wind velocity or the wind speed and the fetch. So fetch is the distance over which the wind is blowing. So for example, your reservoir has a length of 10 kilometers, then the wind is blowing over a fetch of 10 kilometers. And let us say the wind is blowing at a velocity of 150 kilometers per hour. So then your wave height is going to be a function of the wind velocity and the fetch of the reservoir. And again, the wave height is going to be different for different fetches. So we have empirical equations for HW when the fetch is less than 32 kilometers and when the fetch is more than 32 kilometers. You have two different equations for calculating HW. So this you can refer back to gravity dams on how to calculate HW. So once we calculate HW, then the minimum freeboard required for earthen dams is at least 1.5 times the wave height HW. So you have HW and you multiply that with a factor 1.5. So this is the minimum freeboard that you need to provide for earthen embankment dams. Now you could also provide minimum freeboard based on some rule of thumbs, and these are developed based on observation. So, and these are based on the type of spillway. For example, you don't have any gates for the spillway, so you construct a spillway and the design is such that you do not require any gates for operating the spillway, then it is called uncontrolled. So uncontrolled is when you do not have any gates. Then the minimum freeboard should be between 2 to 3 meters. And if the spillway is controlled, meaning you have gates to allow the discharge to the downstream, then if the dam height is less than 60 meters, the minimum freeboard should be 2.5 meters. And for the same controlled spillways, if the dam height is more than 60 meters, then the minimum freeboard should be 3 meters. So you should at least provide 3 meters of freeboard for controlled gates, controlled spillways. So let's say this is your embankment and you have your spillway starting from here. So you can have some gates on top of the spillway. So the minimum freeboard should be at least 3 meters above the gates. So this is the top level of the gate, and your embankment should be at this level, so that there is at least 3 meters on top of the gates. And the minimum freeboard should be the max of 1.5 HW and the condition that is provided in the table. So you should provide at least the maximum of these two values. And the next criteria is the top width. So how much should this top width be for the earthen embankments? So for gravity dams, what we did was to assume the top width based on the purpose that we want to make on the top of the dam. For example, if I want to provide a one-lane road on top of the dam, then my top width would be dependent on the width of the lane. So if the width of the lane is, let's say, 3.5 meters, then I provide some shoulders on either sides. It could be 1.5 meters altogether. So I make the top width as 5 meters. So it is the similar case for earthen dams as well. So the top width is dependent on the purpose that you want to utilize on top of the dam. So if you want to provide a one-lane road, then you can provide 3.5 meters plus 1.5, which is 5 meters. Or if you want to provide two-lane road, then you need to increase the top width. So it depends on the purpose on top of the dam. Or you could use some empirical equations that are given in the literature. So the top width should be h by 5 plus 3, where h is the height of the embankment.
Yeah.
Yeah.
So b is dependent on the height of embankment, which is h by 5 plus 3. Or you can also use these two different equations for when the height is less than 30 meters or height is more than 30 meters. So, but still the top width is dependent on the height of the embankment. And then side slopes. So for side slopes, we begin with these provided guidelines on the what should be the upstream slope and the downstream slope. For example, if you are using homogeneous embankment, then the upstream slope and the downstream slope is dependent on the type of material that you use. So if you are using well-graded sand or coarse silt or silty clay, then your upstream and downstream slopes are changing according to this. Or if you are providing or planning to provide a core or a diaphragm in the embankment, which is for zoned embankments, and this is a diaphragm embankment, then this is what the upstream and downstream slopes should be. Now, these are only the preliminary calculations for the section of the embankment. So what we have is the freeboard and the width and side slopes. For example, I know the water level in the reservoir is going to be 100 meters. And let's say I want to provide a freeboard of 3 meters. So then I know the height of the embankment is 300 meters. And the top width, I want to provide a single lane road. So the top width would be 5 meters. And the side slopes on the upstream side, the slope is, let's say, 2:1. And on the downstream, the slope is 2:1. Then based on these dimensions, we can sketch the embankment section. So I have 5 meters here on the top, and then I have a height which is, sorry, this should be 103 meters. So the height is 103 meters. And based on the slopes, which is 1:2 on the upstream and 1:2 on the downstream, so 2 horizontal to 1 vertical. So you can calculate this width, and you can also calculate this width. So now you have the total width of the channel, which is, let's say I say this x plus 5 plus x. So that is 2x plus 5 meters is the total width of the embankment. So now you have a preliminary section of the embankment where you know the top width, you know the side slopes, you know the height, and you know the bottom width. So this is our preliminary embankment section. And for this section, what we need to do is to check for seepage and also do stability analysis on this section. And once we are sure that there is no potential for failure because of seepage, and if the dam is going to be stable according to our calculations, then we can approve the design of this embankment section. But if we find out that the dam is not able to withstand any stresses, or if the dam is not going to be stable, then we need to revise these dimensions. So this is going to be a trial and error method where you start with some preliminary dimensions for the embankment and check for the stability of this embankment. And if the embankment is not stable, then you try to redesign the embankment. So it is going to be an iterative process. So this, the analysis, the seepage analysis and the stability of the embankments, we are going to do in the next 2 lectures. So the next lecture is going to be on Monday. And today, whoever has the tutorial, I think CE3, we are going to do the problems on gravity dams. So this is all for today's lecture. Any questions on this so far? Are there any questions on this? So I'm going to upload this lecture notes on Google Classroom today, and the solutions for questions 1 to 4 in the tutorial I will provide it by the weekend. So if there are no questions, then I will see you on Monday in our next lecture. All right, thanks everyone. I'm going to close the session if there are no questions.
Excuse me, sir.
Thank you.